welcome everyone. Today we have Nick talking about Markov chains.
Yeah, not just Markov chains, but Markov chains in this new biological evolution blog that Steven wrote. There's like one chapter about that my favorite part of the whole blog about the probabilistic analysis of all these biological models that we were exploring. But before we go into there, right? It's just halfway through the blog, but just to give some context about what's happening, right? What we are doing here. We calling those things, those little creatures over there, adaptive cellular automatons. They're like cellular automatons, but we evolve them to like it is similar how biological mutation work. We mutate some genotype, which is just a rule, which is just a bit string, right? The usual cellular automata bit string. We can flip some bits so that it has some different behavior, and then we just run this behavior, this rule on some simple initial condition like a single cell at the beginning of that plot over here and run it for until it basically stops. So it's like a busy beaver, so it has to terminate at some point, or maybe it's undecidable, so we kind of have some cut that we of how many maximal steps we run, but we look when we look for those, but basically we search for such rules that terminate with this single initial condition. So this is like our fitness. The longer it goes, this is like a fitness function in evolution. So the longer the creature is, the larger it is, so it's more fitter. So that's how we can define the fitness relation, the fitness function for these simple models, right? So we evolve those, right, from this single rule, which is just a no rule, just doesn't do anything, just produces zero, no matter what is the input. We can flip some bits, and we only allow to change it when the fitness actually increases. So we never allow the decrease in fitness. So we have these things like mutation graphs, right? This is a perfect example of what's happening, right? Somewhere over here is a no rule here, I think, right? Again, that doesn't do anything, but all the connections here to all other critters, which is a one-dimensional cellular automatons, of radius 2, I believe, 2 color, radius 2 cellular automatons. All of those connections, undirected connections, are the mutations. So we just show how this rule is connected to this one, is if it's connected, if you can go from one to another by single mutation. But it's actually more trickier because it's like maybe we bunch them down into, because there are more rules that produce the same picture, the same phenotype. So we call genotype is the rule itself. It's just the bits that define the rule, right? Like maybe somewhere on top of that is this, right? It's just the rules. It just tell you how to produce the next cell out of the previous cells. That's the genotype. But the phenotype is that picture that it produces from the initial black cell, right? So and multiple rules can produce the same picture. So in a way, you can mutate the genotype, you can mutate the rule, but without changing its phenotype. So the fitness stays the same. So to a single picture in this mutation graph, there may be associated multiple genotypes. Right?
Can I ask something quickly?
Yeah.
What is fitness here? How is fitness?
In this graph, fitness is not shown anyway, because you just have undirected edges that only show the mutation. So you can mutate from that picture to that picture, but there's no directionality applied to that, right? We don't impose any directionality by fitness. It's what happens, for example, in this kind of graph, when I think we apply some fitness, again, just the lifetime, how long the creature is, right?
Well, yeah, that was my question. So it was more basic. So what are we calling fitness in this context? Is it
just the size of that, the length?
Just the length.
So yeah, how many steps it runs until it terminates.
Okay.
Right.
And so we throw out the ones that go on forever. Yeah,
we throw them out. We assume it's like cancerous thing, right? So it's like also does not survive. So we only have these finite size creatures in a way, right?
Okay.
But it's like one-dimensional.
Right.
So it's 1 + 1 dimensional picture. But
how do you throw them out? How do you know that they are non-terminating?
But we don't know. We just I said that we just have some maximum cutout. Like we
Okay.
run it for maybe 10,000 steps, and if it's still not terminated, we assume it runs forever, right? Or we can actually do it more clever in some cases.
Mhm.
It's kind of obvious. You can just
Sure.
look at some of them, yeah, because it's like maybe some have some cycles and all that.
Mhm.
Yeah. But that's how we do it. So I think basically this plot shows all of the possible phenotypes. Maybe not this one. I think I had some like this one. It also shows like same fitness. Is it? It's not same fitness. I'm not sure why. I don't remember. It's like there are multiple subtleties, like even Steven describes it, but there's another subtlety and another subtlety, and there's like, but even this isn't the end of all subtleties. Basically, there's more details one has to read through in order to understand what actually those pictures are and what they represent. Right? For now, it's just you have to understand there's a mutation relations. We're mutating the rules, mutating the genotypes that can produce the phenotype by running the rule, but we also can assign to each of those phenotypes some fitness, and we can also impose some directionality to this mutation graphs, and that's how we get our evolution multi-way graphs. So we can
Right.
say that we can only evolve in that direction, and we're not allowed to go back in the decreasing fitness direction. We have to only increase it, right?
Uh-huh. And so just for clarity of the audience and myself, the analogy here is that you have kind of a genetic code, which is your set of rules, and even abstracting away that this is a one-dimensional cellular automaton or whatever, you have your set of rules as your genetics. You have always the same initial condition, right? Where you
Yeah.
have and you effectively have ontogeny, right? Like you generate the being out of the genetics from the initial starting point, right? That's kind
Yeah.
of the analogy that you have in your mind.
Yeah, it's like it's growing. Yep.
Yes.
Yeah. Even though it's in a CA terms, it's kind of one dimensional thing, right? Because it's just one state, and you evolve it in time and just see what state it took at every time. But we can also think that it's actually something is growing, right? And we and produces some phenotype and final lifetime. But you can also choose different fitness functions. Like I think this is the exact picture.
But yeah, so I think that's interesting. Okay, right. So I understand that you get some very cursory analogies with something like height or width or whatever.
Yeah.
But I think it's important to know what is being considered, whether you have the evolution of like stepwise evolution of the whole thing as the lifetime of the being, or that thing as the being in for a given fitness. Does it matter that we
No,
think?
well, as soon as you fix the initial condition, like we don't touch it. Well, at least in this chapter, there's
Yeah.
a separate one. We assume that all the evolution that terminates is our phenotype. I guess you have to define it, right? On which,
Right. So that's what I mean. That's what I meant ontogeny, right? Because like many biological beings, especially animals, right? Like they grow into the adult form, and then the adult is kind of a set thing, and normally you have an initial condition and a genotype, and that kind of determines in some way how you're going to get there. But in a way, the phenotype of a time slice is not the same thing as the whole time evolution of the that got you there.
that's why we could have as well like took the last state, just the last row, but it would be that interesting. It's just I think it doesn't matter. It's like
Okay.
you can assume that it's like just like doing some sediment. You started with a single cell and it evolves. It is described by some basic model. It's just right.
Okay,
It,
sure.
it's just accumulating it in a way.
And so the height and width is the maximum at like throughout the process,
Height,
not
yeah, the height is basically the height of that picture. So it's the how many time steps do we run the CA, right? And the width is how wide it got, right? So it's you can impose these two different fitness functions. And we've also been exploring like aspect ratios. Like you can also try to define the fitness by arbitrary aspect ratio. Okay, you should be close to 2, right? This is our target. The closer you to the aspect ratio 2, the more fitter you are, right?
And why? So all my questioning is in the same direction, which is this: why are we thinking of those parameters as fitness, right? In what sense are we thinking that those are being well prepared to survive in an environment or something?
Well, it can be arbitrary.
Yeah, it's arbitrary.
You could have chosen the different function. This is just natural ones for the simple model, right? It kind of makes sense. The longer you get, it's like finding a busy beaver, for the Turing machine. People are interested in that, to finding the most like long running one. So in a way, it's more fitter because they're more interesting and more funny looking critters than those that are running for a short amount of time. So it kind of makes sense.
I see. So, but there's no real. So it's just a parameter that you can measure, but there's no real understanding.
Yeah, just a metric. Yeah, it's just no. Well, yes, that's why it's a simple model. You don't have to go into details how well it behaves in the actual natural environment, maybe in the
No. But I'm not saying that it's not unrealistic because it's too simple. What I'm saying is that I'm just seeing a parameter that is kind of intrinsic to how you are coding the thing, right? Like the fact that this thing will have a length or a width, or height or width, is intrinsic to how the thing is coded. But it might, to me, it doesn't kind of speak fitness in some sense. It is a parameter of it for sure. You can measure it, but fitness to me has to do with survival, right? And somehow.
Well, you can assume that there's your survivability depends on how big you are. Simply
Yeah, so
like,
maybe just the way it was done is that this was enumeration of all possible creatures, and these are only the ones that survived. So we basically, right?
Yeah, right. Those are all that survive. There's no other constraints, right? We just look for all the creatures that survive, and then we get the picture for it, and then we can, in principle, compute any function on that. We can run it through the neural network and compute some big vector and maybe determine how beautiful it is or whatever, or how many holes it has. It's like the possibilities are there are many possibilities there, but the simplest one is just compute how big it is.
Okay, I see.
Right. Maybe we can turn it into a actual model and make it run in some 3D simulation. Maybe this has like 2 legs, it would run better. That would be a fit of one.
Yeah, or make it look like a picture, make it look like a cat or something.
Yeah, something like this. Yeah, that's something that has wings. Or it would fall slower if you drop it into gravity. Well, or whatever. Anyway, so, but now I guess we can skip a lot of it. For now, I wanted to tell about how you can analyze this kind of thing in more detail, this evolution process in terms of probabilities and things like that. It's like there's a separate chapter. There's a big block. The big block. Yeah. So the thing that we have, like this is the picture, explains in more detail what actually happens. So I showed you the evolution multivariate graph that you can derive from the mutation graph by applying some fitness to it. And then basically when you have it, you can count all the paths, all possible paths for each rule that you mutate. So you can, for each rule, you just count how many possible paths you can go from that phenotype to that phenotype. Basically, you can do the basic path counting in that graph and just normalize it. And that's how you can get probabilities by just transition probabilities from one state to another. Now you can treat those phenotypes as some Markov states in the Markov chain. Those loops are, you see 2 loops because they have 2 different meanings. Like the gray loop, I think, is just the one that it's like it's still mutating. The underlying rule behind that phenotype is still mutating. It just doesn't change its phenotype, right? But the rule still evolved. It just haven't evolved, in some different thing that produces some different phenotype. And the red loop just shows you that it evolved to something worse, for some reason, something like that, right? So it's completely blocked. It evolved to a phenotype with a smaller fitness, something like that, if I remember correctly. Basically, just to distinguish some two different transitions.
And this
Right,
is
and
this is single point mutation for the rule set.
Like this is already aggregated. Like there's a maybe there's a plot. Like this is like a giant matrix because you can enumerate all possible rules. Maybe there are 2 to the 19th possible rules, 2 color radius 2 rules that are there, and symmetric rules. You can also drop a bunch of them based on symmetry. So there are so that many total possible rules, and you can just mutate all of them, right, and see and just by pure mutation graph, you can compute all the probabilities. It's gonna your transition matrix is gonna look like this. But then you can aggregate it because you can actually run this rule on this initial condition and derive the phenotype, and you can aggregate it to the actual pictures that we have, right? And that's the aggregated probabilities already. But that for the actual analysis, you have to do this Markov chain analysis has to be done on the rule level first, because aggregation drops a lot of details. But even though it can be close, right? I think this shows like already the aggregated Markov graph, which is rule based, which is 2 to 19 by 2 into 19 power matrix, pretty large, but it could have been, it is much worse for larger systems. And then you can aggregate each of the rules to get much smaller matrix one. Yep. And then you can basically, using that matrix, you can do the basic Markov chain analysis. It's just, you have a giant matrix, your initial state, the initial state, you start with the null rule, which is just produces 0, no matter what your initial condition is, right? This is your very sparse initial probability distribution. Just put 1 into a single rule, right? And if everything else is 0, and then you just apply this matrix, multiply this matrix by you see, this is like a time series of that process. At time step 1, you have all probability into that rule. Everything else is not populated at all. You only have one creature at this particular moment at step number 0, right? But when you apply a single matrix one time to that vector, you get a new vector, you get all the probabilities, how probable is all other state, right? And you apply it multiple times until it reaches some stationary distribution. So further down this to the right, it just has every probability is in equilibrium. So we get all the creatures that actually survive after infinite amount of time, basically. Right? This is just a zoomed version into this region. Shows you that some of the creatures at first survive very nice, very good survivors, and they because they can mutate, basically not because they get killed by a competition or whatever, but purely because there is a mutation possible to become better. This particular creature becomes less dominant if you evolve and wait for longer, right? And this shows the final stationary distribution, so the one that you get at the right. So this is like the most populous creatures that you get, right? This is like more than 20% probability that you will evolve into that if you just follow random mutations. And increase your fitness. I think I have a picture. Like there's a lot of working notebooks that I have. Like this, for example, if you don't have any fitness, obviously there's no reason to move at all. So basically, the only 2 rules would be populated a little bit. There is no reason to increase. So there would be stationary distribution, just having those, and everything else basically 0. This also shows for other fitness levels. Those are exactly those aspect ratios. Maybe if you want to follow, if your fitness is defined, you better if your aspect ratio is closer to this value or this value or this value, and then you get different kind of evolutions, right? And different creatures surviving at the end when the equilibrium is reached. Yeah, there are more plots like that. This is like some river plot that shows how those probabilities evolve maybe in a better way, right? So that you can see at each time how it's more. It's like the more width this this river has, the more probable at that moment it was. Yeah, those are the aspect ratios, fitness levels. This is the previous ones just involved symmetric rules. All the creatures was symmetric. It just was a natural way to thin the number of rules out a little bit so that it's much more workable. There are 2 to the 19th power number of rules when you just have symmetric ones, but as soon as you have all the rules with the same number of cows and the same radius, there is much more of them, and the analysis become much harder because the matrix is going to be larger, right? But you can still do it for this case, at least more problematic, but still there's like more possible creatures involved, right? They have like this non-symmetric but much longer bodies, and yeah, the same kind of analysis holds there. I think this is just the plot point, the bubble plot, almost like based on frequency and lifetime. You see there's like, this is the most fit individuals over there on the right, right? Because but the probability is actually not that good, right? Well, there are much more probable ones over there. This is the frequency, so the higher you go, the more frequent it is, the more probable the individual is. Also, I think was an island there of the creatures that completely do not survive, so their probability is 0 when the equilibrium is reached. So it's like, this is just ones that survive, but with a very tiny probability. Maybe if you actually run this longer, maybe even they will be dropped to 0. I don't know. It's not easy to run it to the equilibrium. You have to multiply it many times. So maybe it looks like this, but maybe it's not yet reached it. But there is a limit. It's like all the question how asymptotics behave there. Yeah, I don't know. You can ask some questions here about this thing.
Yeah. I mean, I was gonna say something that is kind of tangential to this specific. I mean, I can see the excitement of the analogy for biology, that I can see the analogy very explicitly, so it's cool. But then I was thinking about just general rewrite systems, right? Because this is just automata with a very specific setup, right? But I guess this kind of makes sense for any rewrite system, right? You have, as long as you have a notion of deformation of a rule, what you call mutations here.
We did this for the Turing machines. They're dent. Basically the same kind of thing. This is 2D version of the Cellular Automaton, but this is the Turing machine. Yeah.
Yeah, exactly. So what I'm saying is, it is interesting to consider. I'm connecting it back to some other ideas that we've had for even in the sort of physics project stuff, like an observer theory like things. If you're thinking of a mutation in a way is kind of a change in the space of changes, right?
Space in it. Kinda, yeah, because we evolve in rules.
Right.
In sense.
Right.
Yeah.
So I was wondering, I mean, what was coming to mind was, if you are, like, you're not trying to do something that evolves or adapts, like you're just analyzing some good old rewrite system, like the hypergraphs that we deal with, you know, in observer theory or the physics or infrageometry or whatever. You have those. It might be the right tool to think about, you know, if I have this specific rewrite system with this initial state, this set of rules that can apply, it might make sense to analyze it under the kind of deformation of the rules, meaning, you know, essentially this kind of graph, right, where you're saying, if I change my rule in all possible ways with deformation radius, whatever, right, like meaning maybe you only change one connectivity parameter of the rule or something. You know, like you're only allowed to change one node or one edge or something like that.
What do you mean the connectivity of the rule itself?
Yeah, like the rule is defined by some hypergraphs, right? Like just generally.
Okay, in that sense, yes.
Yes. I mean, some terms, right? Like it doesn't have to be hypergraphs, but I'm having, you know, bringing hypergraphs as it's kind of like the template for this.
You have to define what mutation is.
Exactly. You have to define what mutation is, but I think that when you have terms that are discrete in some sense, that these are essentially just enumerations of adjacency data, like hypergraphs, or they are trees with symbols or whatever. You know, like in all these cases, maybe there is a sufficiently well-defined notion that is quite general that means that this is a minimum deformation of your rule somehow. And then you might be able to take that notion and quantify how much of a deformation it is, right? And then you essentially create effectively these graphs, right? Like where you have your initial state, you have how the rule would apply, and then how all the mutations of the rule would apply. And that will give you a bunch of other future states of the mutated rules. And that might give you a sense of derivative, right? Like a sense of change, because, right? And the thing is, you could measure it exactly with these kinds of probabilities that you describe, right? Because, you know, what I'm thinking specifically is exactly what you described, that you have a set of rules, you change it somehow, and the output doesn't change, the phenotype doesn't change, right? Like the output states don't change. So
Yeah.
that's exactly like, you know, this is being preserved, right? Something is constant here. So you just differentiated the thing along a non-changing variable, right? So that's kind of the analogy I have in mind.
They even we have some plots like this, like step plots that show how it jumps, the fitness jumps. Where is this? Like with the red dots. Is it this? Oh, you had a better version. Oh, come on. Where is that?
It's down a little bit. I think it passed it.
I think it's like
Oh, there it is. There it is.
for this. Yeah, it's like how it jumps. It's like how many steps you run it, right? It's like this plateau is exactly non-changing phenotype, but changing genotypes, right? It's just from so many times you have to evolve the rule until it actually can increase your fitness.
Wait, so do they get to the same? I mean, that's the length, but do they get to the same pattern?
Well, not necessarily. It depends. Like the graph has multiple termination nodes, right? But I think this is just shows the maximum. The line shows the maximum, but there's other termination nodes that are not maximum.
No, because what I'm interested in is that you're assigning this, as I said, this quantity that is directly measurable out of the what you're calling the fitness, which is in this case the height of the phenotype or something, right?
Yes. Yep.
So, but you could have something. I mean, maybe I missed what you said earlier, but you could have like explicit phenotype invariance, right? Not just fitness invariance, but phenotype invariance, right?
Oh,
After
yes,
mutation.
because different rules can produce the same picture.
Exactly. That's what I mean, right?
Yeah.
So so I think that's what I was thinking of more for the general application, not with the biological analogy in mind, but just generally studying rewrite systems. That will be quite interesting, because if you have a rewrite system that evolves in a certain way, you generate its, you know, directed graph of causal relations, and then you change your rule in several ways that are directly quantifiable and enumerable, right? Then you might get deviations from that same causal graph that you had, right? And there might be deviations that change nothing, and so you get back the same thing. So that's how I understood your, like, the probabilities that you drew in a graph.
The different kind of loops. Yes, exactly.
Yeah. Like,
You're allowed to stay fitness neutral. I think that's what we were calling it.
yes.
And you're changing your even phenotype neutral too, right? You're changing
Yes.
your
Yes. Yes.
like both. There's either
Yeah.
type of fitness.
I think it'll be, it is, I don't know, I'm just mentioning this because we were in several conversations in the last few months trying to come up with what it means to do derivatives in rule space, so to speak, right? Like which is a bit like doing time derivatives. And to me, this is coming very close, right? Because it's saying if you changed the way that you're going to evolve in certain concrete ways, you can then evolve with those under those changes, and then you can measure the difference of difference, whatever, with one way and the other, and that can give you a kind of a quantification of
The transition probability is your quantification here, right? In some sense.
Well, yes, but what I'm trying to say is you have, it's more like to analyze a single rule or a single set of rules applied to a single state. With this kind of idea of mutation of rules, you might be able to identify this notion of invariance, right? What will remain constant, right? Because if you change, if you mutate your rules, then and you get a bunch of rules that are different, but they produce the same causal graph of the rewrite system, right? Then you know that those rules were not special somehow. So anyway,
yeah, a rule, because we when you fix this initial condition, your rule is almost not distinguishable from like the whole evolution of that rule applied to that initial condition. So it's just the way we evolve it. The fact that it has to be run, it's more like, I don't know, just a reduction in complexity. Right?
Correct. Yes. So I'm not saying that this implies something deep for this work, but I think you could take this idea, and when you're out in the wild doing rewriting for some purpose, like we many times do in our projects, it might be interesting to think of it as, I have a state that might be very large, like some big hypergraph or something. And you might want to know, without needing to like run very, very big computations, you might want to know things like, okay, what are the constant directions of change in here? Like what is being preserved in my evolution? So for that, you might want to, instead of running time forward, you kind of freeze time and you say, well, if you change things about how you're going to evolve, this is how things will change, and you just need to change like one time step ahead, basically, because everything that gives you the same next step is already candidate for that's keeping things constant. Anyway, I just thought it was a pretty interesting idea.
Yeah. Well, I've been thinking about myself how this kind of analogy of this biological evolution and probability analysis, because I like probability in the case, like I've been looking into how it involves how it works out in quantum theories, right? How the probabilities changes there and how it applies to physics project and all that. And the analogy from this biological analysis case kind of has some insights into that too also, right? Because now we can describe like what does it mean for a quantum state to be, how you can derive basically the properties of quantum properties from the biological evolution, even without explicitly putting them into that model, right?
Yeah.
Just from pure probabilities. Like this is Markov chain, just purely classical probability theory, right? Just states evolving from one to another, which is just mutation. But when you apply the fitness, you kind of impose this directionality of how you evolve. You kind of try to impose this total order on all of the states right? So that you can differentiate between what was the initial state, the initial distribution over some critters, and the final distribution over some critters, so that you can now describe some dynamics, given that fitness, even though your fitness just describes just like whether you're allowed to move or not, right? But even though if you have just a random walk on the mutation graph without any fitness, it can, as soon as you apply this fit, basically what I'm saying, this fitness can basically in more fundamental physics can act as an arrow of time, just from evolution from the initial to the final state. But this dynamics, in a way, when it tries to preserve some form of information or whatever it is, so that it's, and there is also some kind of constraint in your uncertainty, things like that, then you can derive the quantum theory. So that's kind of the hope here and how the analogy works. So it's like basically the same kind of probabilistic analysis plus some uncertainty constraints, and you should be able to explain and derive Hilbert space even, I hope.
But do you think that there will be it will be quite sensitive to the rules themselves?
Not really. No, just as soon as you have these constraints on your probabilities, right? And you will able to probabilistically make this probabilistic analysis, then I think it's okay. It would correspond to some actual Hamiltonian. That's why my intuition is telling me, but I still don't know. But that's a very far-fetched for now.
Yeah, but it does feel like I mean, how much did you guys think about like rule mutation when thinking about this whole story of, you know, branchial space being kind of the analog to quantum and so on?
What's more like if you have a random rule mutation, it's like a random walk without any it's like just having a single roulette kind of thing. You just slice through the roulette and you enumerate all possible states and all possible single cell mutation between them, which is like, okay, this is our computation. So it's just one example of the slicing the roulette in a way, right? And then we can analyze it in this similar way. Okay, as soon as we sliced it, we can define or count all the possible transitions from one state to another and compute some kind of stationary distributions and transitions between initial to final ones and how those evolve, right? The point is that the transitions, because they like act as mutation and you have a random walk, they go back and forth, right? The analogy of this backwards and forward evolution, when your fitness is actually has this arrow of time kind of property, that then this backward evolution has exactly the same signature as you have in like quantum theories, when you have to have this backward signaling, backward transform, like backward, what's the name? Whatever, backwards and forward message passing.
Yeah.
In order to derive the actual probabilities that we observe in experiments.
Yeah. Right. So we are agreeing that there is something here that might contribute kind of a new perspective.
Yeah, that's what. Well, that's the whole thing about being computational X. Yes, we hope it's just this graph properties of all kind of models are the underlying theme of all of that: physics, biology, maybe mathematics, right?
Yeah.
We're closing in on biology this time. So we did a little bit of physics, a little bit of mathematics. Now it's kind of this graph analogy makes sense and can shed some light into those, both physics and mathematics.
But what I'm not, what I'm wondering is, I feel like there has to be some kind of dependence on, and my intuition is that if you assume, like, if your system were very different, like the substrate of your beings here was something else, right? And you assumed different possible rules. Like obviously the methodology is the same, like the analysis is always the same, and that's the principle that we want to export to other areas. But what you observe specifically is going to depend a lot on what rules you assume, right? And what specific slice of the Rulliad you're taking, if you want to phrase it that way.
Well, yeah, that's where the things like computational equivalence things come over, because it doesn't matter what you slice it, as soon as you slice a computationally universal thing out. That's something like that. Maybe because the rules that you produce can emulate other rules in that sense. The fact that you sliced it that particular way of mutating your rules or that particular computational model doesn't matter, as soon as it's universal. Like, I don't know whether this one is universal, probably not, just kind of looks weird, but yeah, in general you can study like universal rules,
Right.
even but their kind of multi-way graphs gonna be infinite.
Yeah,
because-
but I'm thinking very concrete terms, like this offers, like imagine if you were in the business of finding just like essentially these Markov chains, this probability distributions, right? Like this sequences of probability distributions effectively, right? Imagine that, because I mean many times in quantum information that's what people are doing, right? Like the Bell inequalities are essentially that, right? Like you have some probability distributions and you do some experiments and then you see if they match or not, right? That's kind of a
Yep, kind of.
very description of what's going on there, right? But
Yeah.
so and you know, if you want to derive the quantum probabilities, right? So far, you know, the parents of the quantum theory, you know, told us, yeah, do this thing, you know, complex numbers, matrices this way, Hilbert spaces this other way, blah blah blah. Like you do all that, and then you end up with probability distributions, right? And I take this from your live streams as well, Nick, where you just shown the qubits as probability distributions and so on, and like putting it on equal footing to more classical distributions and whatnot. So imagine that you're in the business for that. Now, I think this offers kind of a bit of an industry of how to generate those things in a controlled way, right? Because if you have a set of rules, and I don't even care if these are hypergraphs or automata, like doesn't matter. But you have some substrate, you are going to assume like some states, and you're going to assume some range of rules, right? You can basically just generate a bunch of probability distributions out of these. And I think it would be interesting to know, you know, if you want to think that these are models for physics, maybe because you're in the context of the physics project or something like that, but maybe not. It makes sense to like say, yeah, let's generate probability distributions out of these things that essentially come from a very different black box thing, instead of being, you know, Hilbert spaces with this specific thing and blah, blah, blah. And, you know, they come from another abstract thing, which is these finite discrete rules that are very abstract in some sense. They're very minimalistic, and they don't, for a human, it doesn't seem to have a lot of information. But, you know, ask a human what information does it make to have like a two-dimensional Hilbert space with this and that, right? Like it doesn't immediately like say, oh yeah, that's why we should be using it for qubits, you know. It just works, and we just use it because it works. So do you agree that there's a possibility here that we might be finding a way to like systematically and controllably generate a bunch of probability distributions? Just
maybe I don't have like a recipe for that, but it would be nice to have just like you said, Bell inequalities, just to have this nice setup, because you know there you have initial probabilities basically and your final probability, and you have the dynamics, which is usually Hilbert space, right? And you have to some notion of locality, but there's no stopping you to describe this as your initial state and final state as a joint state of probability distribution, right? You can have this joint one that marginalizing the joint one gets you the initial and the final one, right? As soon as you have find some underlying rules that produce this Markov chain with a distribution that produces this joint one, right? You can kind of then ask question, how would can I like just prescribe this arrow of time there and describe the dynamics, how they, even though it's like goes back and forth between final it's because it's timeless. But if you want to assign some time directionality, how it actually evolves, what is the dynamics, what is the dynamics governed by this rule that you just had, even though they're timeless in a way, but as soon as you prescribe the direction,
Right.
the dynamics is much more different, and you can study properties of that dynamics instead.
Yeah, yeah, but even in very practical terms, right? Imagine and tell me if your intuition is compatible with what I'm going to say, but imagine that you want to calculate like physics. I mean, physics about predictions, right? Like we go to the lab, we do some preparation, and then we have a theoretical model that represents that preparation somehow in our symbolic system, maybe Hilbert space, some manifold, whatever, some code in some computer, some LLM, doesn't matter, right? Like we have some representation of that initial state. And then we run our things, our formalism gets to work, and the formalism basically tells us, hey, if this wasn't your initial state, these are your probabilities for outcomes that you're going to get, right? And then we go on in reality and we run the experiment 100 times or 1,000,000 times or whatever, and we get a statistical distribution, and then we match the probability to the statistics, right? I'm just saying something completely trivial for most people, but it's important to get the point across, right? So you have that. Science kind of doesn't care what you did to generate that probability distribution to match to the statistics, right?
Yep.
So am I right to say that it might be worth exploring simply black boxing this, because this is another way to get, it's another controllable, discrete, finitary way to just like mathematics is, you know, our mathematical methods, to generate transitions between probability states, right? So it might be worth just thinking, hey, which are the ones that actually produce the probability dynamics that we observe, say, in double slit experiment or in whatever, you know, like in real world experiments.
Yeah,
right?
I had like this example about when I was presenting about the Bohmian computation. It's just a single qubit evolving, right? But as soon as you fix the initial final probability distributions, the Bohmian view provides you how this dynamics actually works out in the middle. Even though the quantum theory just says, okay, you apply this thing, you can do the Born rule and you get the probabilities. But if you apply the Bohmian computation view, you have the stochastic laws in the middle. So you can get the transition probability at every time step in the middle. So it kind of tells you more, even though it doesn't provide anything new for your experiments. It still describes more of the physics in that, right?
Sure.
Even though the pragmatic people wouldn't care.
Right. But even I'm thinking that even what might be quite I mean, I don't know how easy it is to come across ways of generating discrete controllable probability dynamics or just probability distributions. I mean, obviously you can pull them off of a hat and like, but there's no sophistication there. But here is much more like if you have a way to say, hey, these are your variables for your problem, and I'm going to encode them as these particular states in my kind of computational system, rewriting or whatever, hypergraphs or whatever. And then I'm going to run with these specific rules, and I'm going to, or this specific framework, because I think it will have to do with not just specific rules, but like rules on how they mutate or whatever, you know, how their secondary change or whatever. And then you generate these probabilities, and then you make a prediction about how the system is going to evolve. And then you match it with the experiment. So imagine if you discovered something like, hey, we can get classical probabilities with this kind of rules. We can get quantum probabilities with these kinds of rules. We can, you know, something like that. That I think would be pretty impressive if you could do something like that. Because in a way, it's like, how to say, it's like, I mean, maybe I'm just sort of rephrasing the whole endeavor of, I don't know, discrete physics or digital physics or something where you're basically trying to encapsulate what we have done so far with continuous mathematics and differential geometry, Hilbert spaces, and so on, and you might be able to encapsulate it with something that is equally computable, something that is equally scalable. You know, you can build big computers to do your computations for you, but nonetheless relies on a kind of symbolic framework that is completely alien, that we don't understand because it's some like weird, whatever, network model or hypergraphs or this whatever, right?
But hopefully it's still based on in physics in some way, because just coming up with some computational model that reproduces your experiment, right? Probabilistic probabilities from the experiment, I think is not enough. That's like, I think it has to be some physical analysis in there. Like we don't have to like replace everything with hypergraph rewriting. Maybe it has to be look more like particles in some sense always, right? If we were actually modeling them. That's, I don't know.
But in any case, so you're talking about having models for probabilities and then seeing if they test out as a like prediction, I guess. I mean, the point of this this post was it was like a purely empirical search out into the rule space, right? And we just kind of see what we get. Like there's no predictive like measurements that were
No.
Well, but
Yeah.
the post here, yes, but this probabilistic analysis, like at least it can exactly compute the probabilities. Like we won't be able to simulate it exactly, right? By just randomly mutating your rules, you have to do something like that, right? And that's how you get exact probabilities. At least this kind of.
Well, for this one, it's like it was an exhaustive thing because there are only like 500,000 symmetric cases for the K2 R2 kind of thing, right?
Well, you can always it is kind of always exhaustive as soon as you deal with the finite number of states, right?
Well, I mean,
Take a
if
qubit,
it's sufficiently finite, I mean the K2 R2 that rule space is 4 billion, I think, and then the symmetric is down to like 500,000.
Yeah.
And so you could do like an exhaustive search and then get like what the probabilities are in fact for that set. But for the multicolor ones, it's like it's unhinged the number of
Yeah, but my understanding of because the conversation that we were having here was about this probability transition probabilities, right, in the graph below. My understanding is that you don't need to know anything exhaustive or enumerative at scale somehow to begin to generate those probabilities, right? Because the moment you have one initial state and I'm gonna, by the way, I'm gonna say a rule. When I say a rule, I mean really potentially several rules together, right? Like, I'm just gonna say a rule. So when you have an initial state and a rule, and you alter, and you have a well-defined way of modifying your rule, this so-called mutation in this context, right? If you have that, you can control how you generate, like obviously no mutation, you get the same thing, but one, so mutation of depth 1 will get you this many new states, and you can start to run probabilities on those, right? Because you would get ratios of this many new rules correspond to the same new rewritten state, right? And so etc., right? Like, so the whole idea is that you don't have to. What I find powerful about this idea is that you just completely neglect the question of enumeration or being exhaustive or anything like that, because it's just immaterial to the point of actually finding probabilities. Because the moment if your states are finite and your rules are finite, these sets are always finite, and if they are small, you want to think that in some scale they're going to remain small to some degree, and very easily computable for like for unit changes, right? Like you say, I mutate with 1 unit, whatever that means in each context, right? Or I mutate with 2 units and so on. And so to me, that's kind of what made this very enticing, that you could have this kind of I don't know how to call it, like mutation, deformation of your rules, and that immediately spawns probability distributions out of a given state and rule, right? And so I don't know. I mean, that to me that is kind of an interesting situation, because previously you were always thinking, here's a rule, here's a state, and then here's like n states that come out of that state given a rule, because that's all the possible ways the rule can act on the state. And many times we were thinking of that as kind of like maybe encoding some non-determinism, right? Because it has like many branches or something. But maybe that's kind of, but in itself it was fully deterministic because every rewrite was fully deterministic in itself, right? But if now we are thinking of the rule and the possible applications as the single output, and then the rule modification as the change, then you are getting probabilities on the dynamics of the system, right? Which is yeah. Anyway,
in a way, yeah. If you just simply think of this is like a way to get some probability distribution out of just having a rule. You can then ask, okay, if, for example, quantum theory is all about how distributions evolve, or statistical mechanics even, right? You can also ask questions how the whole underlying computational model changes. Like here's like 2-color radius 2 model of cellular automaton, and it produces this. Actually, we can just do it for initial conditions, right? So we can fix our computational model. Okay, we fixed the type of it, K2R2 cellular automaton, but we can change those initial conditions. And given the initial, there was, yeah. So here, like, we can also evolve the initial condition, right? In a way. And as soon as you change those for different initial conditions, you get different Markov graphs, different probability distributions too, right? So in a way we can just describe dynamics by changing initial conditions, and that will automatically give you different distributions. So in a way, that's also statistical dynamics of sorts. Yeah, that's actually, yeah, that's a good idea. I haven't looked into that.
Yeah, no, I find it honestly quite promising that. So I guess, yeah, next steps will be like, how do you define mutation? Is there a sense in which you can define mutation a bit generally that is not just?
I don't think, like, I don't know, mutation is kind of, I don't think it requires like too much generality. As soon as you have bit strings, for example, it's pretty straightforward what to do, right?
Sure.
Just, yeah, but the dynamics of how those, yeah, I want to think about this initial condition things more in depth, how it relates to probabilities,
Right.
and how probabilities actually evolve after changing initial condition.
Yeah,
Kind
but
of
I mean,
good model.
So I mean, if you say you have bit strings, but I mean, sure, I mean, it's obvious what to do there, but when your data structure changes a bit, I mean, it becomes highly non-obvious what it means to do a mutation, right?
Yes. So, well, if you have a hypergraph or hypergraph rule, if you have a rewriting rule, okay, we can just simple mutation. I don't know, you can just add edges, right? Add vertices, remove vertices. That's kind of
Sure. I mean, the
all the
options are
stuff.
clear what to do
The
exactly.
hypergraph edits. Yeah.
Like the options are clear, but you know, because a rule is kind of a sophisticated thing in hypergraphs. It's not like this simple, you know, one directional thing. It has like moving parts. So I mean, we always talk about how we can just parameterize rules by input output hypergraphs, right? And so it's easy to say, well, we're going to mutate only the input, the output's always going to be the same. But yeah, but it will be interesting. Maybe this is giving us enough motivation to like find a good data structure for I mean, this is an entirely unrelated thing, but like a general data structure for a hypergraph rule that
is mutatable.
that lends itself naturally to being mutated. I mean, because right now, like, yeah, we don't, like, even if you take some mathematical formalism for a rewrite rule, it is highly non-obvious how that is.
It's like too complicated. Let's start with like Wolfram model, right? Just like a list of lists. This is your rule. Treat it as a list and just mutate it. I don't know. Just see what happens. You can do the same kind of thing that we did here for CA and Turing machines, but for hypergraph.
Still, even if it's a list of lists, still unclear fully, right? Because
Well, this is just requires some tinkering. I don't think it like requires some generalization. Just this is more like an exploration of what you can.
No. I mean, this I agree. Yeah, you can do this for Wolfram model for sure. Yeah, I don't see a problem there. But what I find very important in this somehow, for my intuition, because I'm thinking of this as the kind of the time derivatives, right? Like you have your space-like derivatives, which basically are how you change a state to a state. But then you have your time derivatives, which is how you change the rule to rule, because it's what is going to change the state, right? And so it is, to me, quite important in all these games that we play that we have these countable directions that allow us to do like countable processes and to essentially like build all these graphs and all these quantities. You're always counting some things, right? Like there's only counting really. Like it's all this is just like counting of different flavors in different ways. So if we don't have a good way to count that, hey, we just went this many steps out of the rule, right? Which is, it's kind of like, mathematically, you could think of this as, in order to do calculus on a space, you need a topology, right? Like, so our version of that is we need a way to know how to step by step go away from a rule in a definite way, so that there's a sense of like radius or like distance away from rules. You could phrase it very generally as saying, can we define distance between rules? Like that would be like a way to kind of flip the question on its head and just think of it in that sense.
If our rules are hypergraph rewriting rules, and we have some nice distance metrics on graphs, now I guess it also can be generalized to hypergraphs, like edit distance. I think it's the natural Levenstein kind of thing for graphs. How much edits you have to do to the graph, and therefore for the left-hand side and right-hand side of the rule. That's the distance. You just sum them over. That's
Yeah. Again, I mean, I know that it would be in some direction there, but that's what I meant for having a defined data structure that represents the rule, so that you can apply that idea like verbatim, right? You can say, this is my rule represented with this data structure, this is my other rule represented with this data structure, and so I can do this number of edits, and that's the distance. Like, but right now, I guess it's, yeah, maybe. I mean, there's a very literal sense in which we can implement that, right? Where you just take the rule as it is in the language and you like literally go through the possible edits, although I don't know.
yeah.
But yeah, anyway. But something like that. Yeah, but this is quite interesting. I find that there's very, I mean, aside from the implications to biology that I'm sure we'll be exploring in the future in the institute, but I think there are very interesting takeaways from this sort of mutation idea for general rewrite systems and so on. I think it's pretty cool.
Yeah. More to explore here.
Definitely.
Always.
Any thoughts on the biology part? Like, should we mention something? There may be some biologists in the audience who want to. Like, I really like, as I said.
Yeah, I mean, a future direction for like the next like piece that is in the works for like medicine, is to see how well these things are robust to like single point attacks. That is, if you have this cellular automaton, it's doing its thing, you poke one of the cells, one of the squares, and change its value and see like how that affects the thing and whether or not it'll heal around that single point mutation.
I'm just looking at some comments now. There was some Sam was commenting a bunch. Just gonna go for some. Is the transition matrix symmetric? Are there cycles in the Markov chain? There are cycles. Yeah, the Markov chain are kind of cyclic. You can go back and forth between the states, and it is symmetric because you have undirected edges, right? Yes. As you saw in that picture, we have a plot, right, of the matrix itself. This one, it's symmetric. When you aggregate it based on some weird phenotypes, then it's not, because then the rules actually start to differ. Okay, else. If you see some good questions, please let me know what we've missed.
I mean, the other interesting thing that one could think about in terms of the biology direction is that it's basically my first comment earlier that fitness, you want, I mean, all these are kind of placeholder notions of fitness that we're just thinking, oh yeah, we can extract this number, you can come up with any function, but I doubt that evolution actually happens that way, right? Like, I don't think evolution is happening because there's some function maximization or function minimization going on, right? It is
more complicated, yeah.
Yeah, it's an emergent property of like several agents and things like that, right? So it will be quite interesting to see, like, this is a great finitary small computational model for a genotype phenotype sort of thing. So it will be great to actually have those phenotypes do their thing, which they do in the real world, which is to interact with other phenotypes and the environment to select, right?
Yeah. But in a way, it's like all encoded in a fitness function. You can still, even if it goes through all these complicated interactions between phenotypes, you can still assign how well each individual phenotype does, right? It's just it's just still a fitness function that can be applied in a way. Though it's
I don't, well, maybe.
Maybe it like depends on how much competition is there, right? Different kind of distribution of different creators may depend on that. It's not just it's individual, a single individual competes with other individuals, and they're equally likely to be there. That's what would like just a simple thing like height would do. But if it's
sure. Yeah. So yeah, I see what you mean. Like if you define, yeah, but this is starting to look more like a sort of life simulation than what I have in mind. Like if you took each of these entities and you put them in a network, right, with each other, and then you have some equally simplistic, equally like abstract, small, whatever model of competition or not competition, but interaction in general, right? Like you put them in interaction somehow. And I'm just thinking what could be, even in this example of 1D automata, you could maybe come up with something. I don't really know, but yeah, but it is, I mean, in a way, like this whole rewrite philosophy always had this notion of ontogeny kind of built into it, right? Like you have access to a small bit, like a small set of information that you're able to edit quite easily, right? Because it's just a few rules, and then you give an initial state that could possibly always be the same if you want. And by small tweaks on your rules, you might get, you run the thing for many steps and you get big things and potentially very different things with small tweaks to the rules, right? So this whole generative approach that the physics project took, and we've seen in many other areas, kind of has always had a very resonant theme with ontogeny, with this idea that an organism has the genetic material sufficient to give rise to a complete organism, even though, you know, what I'm inspired by is that, you know, so we're gonna have Michael Levin soon come and give a presentation, right? So I'm saying this kind of in preparation to that actually, because what I've learned from Michael's work is that, you know, genetics is not everything. Like you cannot reduce things to genetics, right? Like so genetics has determining power over the dynamics, but they are not all the information that gets that is at play in ontogeny, for example. And there's all these famous I'm sure that we will see this soon in this forum.
Like genes can be activated, like deactivated, right? Based on different environments.
That on the one hand,
that's up to the epigenome.
yeah, and that's on the one hand, there's that, but there's also the fact that there are dynamics that are completely kind of orthogonal to genetics. So Michael very famously shows, you know, how you can intervene just the bioelectricity patterns of like developing like tadpoles, and you can have them grow like limbs or eyes or whatever you want in their body, which is or like you could have like these planarian worms grow like 3 heads or 2 heads or whatever, you know, without touching at all the genome, right? It's not like you are making some genes express or others.
Well, humans do it all the time, right? We transplanting organs. We can have our limbs replaced by artificial ones. It's kind of the same in a way.
Yeah, exactly. So anyway, so I'm thinking in that direction where your phenotype creates an informational space that has its own dynamics. And sure, it is determined by the genotype, right? Because that's where it comes from, kind of causally speaking. But in the sense of informational dynamics, the dynamics happen in the phenotype space, or the virtual space generated by the possible phenotypes. So that's why I thought it would be quite interesting to put these phenotypes in interaction somehow, like because right now the phenotype space doesn't really have that much of a role, right?
Yeah. Oh, it's usually like complicated. That's usually what people do when they talk about evolution. There's always some kind of environment, right? But it's still even in reinforcement learning, there has to be some reward function or whatever it is. But if you want to simplify it, I would like, even with this height fitness, you can imagine that you're not just searching for the highest, the most fit individual. You kind of put it in some ranking with different individuals, so that you can define, okay, this is, even though this is the highest, you know, the highest in the rank, there's some second rank and third rank, and they can also have some saying that, right? In the
Sam asks if these CAs can fight to the death somehow.
Yeah, let's let them fight.
What was the question?
If they can fight to the death, these cellular
yeah, but that's kind of the thing. You know, I don't think we would need to somehow implement a virtual version of environment. I think it would just need to be a way of, so the environment will be naturally the kind of space of possibilities of interactions between these things. And as long as we come up with an extremely simplistic model of interaction, which should be dictated by the data set itself, right? Like the data structure itself. It's like, okay, if these are 1D automata, and I have 2 of them, maybe just the final state, like what is the natural interaction between those 2 things, right? There aren't that many possibilities. These are like discrete kind of like systems that's very small. And then you put all those things in a network, and you let the fitness dynamics emerge simply from some of those very, you know.
Yeah, there's also like a possibility of actually changing the fitness while you're evolving. Like this, we were doing this kind of thing when we just linearly increase the fitness, right? So it has some actual phase transitions basically, because as soon as your fitness reaches some particular level, right, you want this, there's some new possibilities immediately emerge. Like, okay, this individual suddenly became like the best one, right? So it now completely starts rising on our evolution is possible now, right? So there's some clear phase transitions. You can do it in a different way, but you can also do like ask a more complicated dynamics of fitness that may depend on like distribution of all the individuals because we are ranking them and throwing in some virtual environment and they fight there, right?
Yeah.
So that kind of dynamic. So we can start with the single individual again. It can mutate randomly, nothing interfering, but as soon as other individuals start rising, you can rank them together so that now the whole fitness depends on on the current distribution. So basically fitness depending on the distribution. That's kind of minimal version, minimal way of saying it. There's some environment involved.
Definitely, yeah. Yeah, I was thinking. So that's definitely one possibility. I was also thinking about what you could do in terms of rewriting, right? Because like in a way, so in a way, it really matters here if you're thinking of the final state of the automaton or the time lapse of the automaton that takes to, from the initial state to the final one as the kind of organism, or you're thinking of the slice of time that they are in as the organism, right? But in either case, I think you could imagine something like, hey, I have rules, the same as I have my genetics, like the rules of my genetics that decide they generate this thing. I have my own sort of perception and action, like my senses and my muscles, like you have your affordances cognitively, right? Like and those might be like also encoded in rules, but maybe rules that interact. So basically that have two automated states as input and two automated states as output. And somehow you need, like, you know what I mean? Like you carry that information that is part of your state. You carry it, okay, if I find another automaton, apply this, and it's kind of half of the information or something like that. And then the other automaton provides the other half of the information, and that makes a full rule that makes the interaction deterministic, right? And so these two automata states get transformed into these two new ones, which are completely determined by their genetic information and their current state. And so that way you can somehow just evolve the interaction. And again, it's completely minimalistic because you don't know how you don't know how to interpret this at all, right? You don't know but you could still measure height if you want in that game, and you could, if they two interact and one comes higher than the other as a result of the interaction, then you could say that one is winning over the other one. I think we lost Nick.
Oh, I think
Back.
Oh. Yeah. Did you get the last bit?
Well, maybe not the last one.
So
I was talking about
just saying
like an interaction between two things to make a new one, like a sexual process.
Yeah.
Like
so what
play in chess or something. We can.
Yeah. So like
Oh.
the point is, however you implement it, what's interesting about it is that you could still define, say, height as your fitness if you want, and it could remain like how. I mean, you could have this sort of interaction genome, right? Which is basically like how when you encounter another organism, which is another automaton state, how you're going to both react to each other. And so you enter the interaction in these states with these rules, and they act together, and you get out in some other way, right? And that information is fully determined by the two beings, right? Maybe it might be even simpler. Maybe, I just realized that it might be completely. Actually, I don't know why I didn't think of this. So it might be just fully dependent on their state. So there might be one interaction rule, which is basically just a like a 2-input automaton rewrite rule, right? Where you define it as a global thing. You say anytime two automata come together, this is how they interact, and you define it. I mean, two automata states into two automata states, whatever. And you can do enumeration over those rules, and the same way that you do over the rules that generate the phenotypes. And so what I was saying is that you could then generate the time flow of the automata in interaction, right? And in evolution with their own genetics. And then you could add basically you could still measure something like height as a fitness or whatever, right? And you could still see if, when two of these interact based on their states, one is gonna come out taller than the other, right? Or maybe wider, because if it's just one state, that width is what matters here, right? So
maybe you can allow some like perturbations to those rules. Maybe you can, because even it's simple to compare just heights, right? But maybe you can perturb it a little bit, and maybe it can completely destroy itself, right? If you and the heights are actual distribution of heights around this individual are not as high as it seems, because it can immediately evolve to some bad one. It's like
sure,
not stable. What there are many ways you can.
Yeah, but something like that. I realized that maybe the environment is simply like a 2-input rewrite rule for whatever your states are, right? And you can make it higher order. You can make it 3-input, 4-input, doesn't matter. And then you just evolve. You have your states. You make you select some pathway in which you uniquely take pairs of things, and then another step is taking pairs of things again, and like you evolve it in this way, right? Maybe just stochastically, and see what happens, right?
But it's a question for you. It's like, are there any ternary like voting systems? You can like there's an EVO rating in chess, right? Because there are 2 players. But how would you do the ternary version of that?
Ternary version of what?
Of EVO rating in chess. That there's or they do it for like GPTs now, LLMs. Just comparing things with each other and decide the ranking of some things, which is better, right? You can basically totally order. Yeah.
Oh, ELO ranking. That's what you're saying.
Ternary rank.
Yeah.
Oh. Yeah.
The ternary version of that.
Oh, that's very interesting. Actually, in my first paper about arity science, I mentioned that I have like a 3-player chessboard as a
I was about to ask about 3-player chess. So how is that arranged?
Well, I mean,
you play on a hex
principle,
grid almost. Have like
I don't know how you play that.
in.
I mean, it's some kind of hyperbolic plane analog, I think.
That wouldn't be chess, or that would be a different version of the game. I think the question here is an ELO rating between 3 people playing a 2-player game. Is that the question?
No, that's easy.
It's like more voting system. It's like, how do you vote for something, but like, not by comparing 2 things. But
ELO rating between three people with a 2-player game, that's easy because that's just a triangle of ELOs, right? But the question here being raised by Nick is quite an interesting one, because you will have situations where the output of a game, right? If the game is strictly competitive, meaning there are winners and losers, then it's not so difficult, because I mean, a 3-way game where there's a single winner, it's kind of the same as a 2-player game, right? Because you just need to decide the winner.
Well, what if the game is a score that also can be 2 players can tie out of 3? So it's
yeah. That's the interesting part. That when your win states are not simply Boolean, right? And
not even the ranking, right? So that it's 1, 2, 3.
Yeah.
And tie. So
I find that to me is very interesting because, you get into the situation where, the game, the output of a ternary game might have, my intuition is, the outputs of binary games should be binary. Outputs of ternary games should be ternary. Like it sounds like just like kind of a rhyme, but I think there's some interesting mathematics behind that where you might want to treat outcomes of a game with a combinatorics in mind, right?
well, it's not ternary, it's like all possible rankings of start, at least, right?
Yeah,
Because
but
it
that's the thing. But
binary, but it's
but-
ternary, it's like 6 prefactorial.
yeah, that's what I meant. That's what I meant ternary as in like
Yeah.
being within the realm of ternary. But here's the thing: like if you want something completely competitive, then there's actually no escape because you're always going to get something like a ranking, even if you allow for ties. That's still easy to model with a Boolean, conventional Boolean stuff. But what I find very interesting, which is actually very relevant to this whole evolutionary thing, because people do it in ecology a lot, is when you consider three-way interactions or higher order interactions of species, for example, right, that are like symbiotic, right? Symbiotic relationships, they animals or species come together and they perform sort of functions for the group of the symbiosis, and there's no winner or loser. There's just they're interacting, and everyone is winning in some sense, or everyone is losing in some other sense, right? And so that interaction is what actually drove many of the ecologists to look into hypergraphs first. Like there's a relatively long tradition of hypergraph models in ecology exactly because of this point, because the relationship between multiple species that come and interact is usually non-binary. It has this sort of distributed, non-directional, kind of non-binary, non-competitive flavor to it. So when I wrote that paper, I was thinking exactly about this for games. You might have a competitive scenario where maybe Dugan, Nick, and I get into a game, and the output of that game is whatever alpha state, and then maybe when myself, Nick, and James were going to the same ternary game, the output of that game is beta or something, and then you have a different state, and you kind of build up the competitive sort of branching, where with different quantities, and this may be as simple as simply making the space of score higher dimensional, instead of having score be a one-dimensional space where it's just like a ranking. You might want to say that your score space is like two-dimensional, and the outcome of a game is a point in a plane instead of a point in a line, right? So things like that, those are super interesting. Like it's difficult to think about, but it's kind of, and we were also thinking about like economies. This is all very related. Economies where typically a transaction is between two parties, right? But you were interested in modeling economies where the minimal transaction cardinality was 3, where you always needed like 3 intervening parts to perform a transaction.
Yeah, well, this is very interesting because even in economics, like a transaction is maybe or you can even say it's always between two people, but the visibility of that transaction, the information that confers, is available to everyone simultaneously. So every interaction you make has an effect on the group simultaneously.
And also place in the middle.
Yeah. And it's sort of like Elo, because any result of any game that affects an Elo rating has a result on Elo ratings in general. The entire world of chess players' Elo ratings are affected by the result of a single game to whatever small degree. So it's very interesting.
And what I find interesting in this Elo question is that when games, as I said, if games have losers and win or single winners, let's say, if games have single winners or tie states, then things are relatively easy to model because it's not very difficult. It doesn't matter if it's a 2-player game or 3-player game. I mean, effectively everything kind of becomes a free-for-all, even if the interaction between players reduces to kind of pairwise games, right? But like an ELO system is in a way kind of emulating a free-for-all, right? Where like battle royale, where everyone is like on the same field, and you know the top ELO player you imagine is the one that's gonna come out on top and like survive the final round. But what really makes things interesting is when you change the ELO premise of there's single winner or tie state for the games, and then you go into this direction of maybe game state or game termination state is not a Boolean, or is not like kind of a totally ordered variable or something, right? And you give it a different data structure. And I actually played around with the idea of instead of like a totally ordered set, you choose this minimal lattice of 3 elements, which is basically the color algebra, like RGB, white, and black, right? Where you have like RGB, the pairs, you know, the mixed colors, and you know, additive, negative combinations of colors, and white and black. Like that forms a very nice algebra that is like associative, like has very nice algebraic properties, but it just happens to be non-totally ordered, right? Because red, blue, and green, none of them come before any of the others, right? Like you could maybe say that black comes before RGB comes before white, but between those there's a little bit of, so maybe you can have an RGB valued game, right? Where your win state is just valued in this algebra of colors, and then I mean the natural thing is to embed that in a 2-dimensional space or a 3-dimensional space, and like measure things metrically in those spaces, and you know, you can still project down and say who is the best, who's the reddest player in this game or something, you know. But yeah, it's interesting, very, very interesting direction.
I think it like generalizes to total order, generalizes it to some kind of clustering, right?
Right.
Yeah. So you have, instead of just smaller, larger, you have red, green, and blue. So it's like
Yeah,
pre-clusters.
it's almost
Or
like the
then-
number of poles, right? Like if you think it, especially if you have like 2 poles, you know, you have win, lose, right? These are kind of the Boolean poles. In like you could have like distributions of players that are like either closer or further apart from these 2 poles, but suddenly if you throw a third pole in the mix, right, then just the information of more or less is not enough to characterize the system, and you have to say a bit more, like, yeah, and I'm equally distanced between RGB, or I'm much more red than blue, you know. So it's kind of an interesting thing, right? The whole thing kind of changes your mentality. Like humans are very quick to like simplify and quantify and say what is more or less. And I think that's ultimately because we are emotional beings, and our psychology is very much a Boolean psychology, right? Like you are either feeling pleasure or pain. Like it's clearly like physiologically, like your reward function is very much attuned to that, to like
I can be neutral. It can be like,
no, it can be neutral. Sure. It can be neutral, but that's fine, right? Neutral is in the middle, right?
Yeah.
So I'm not saying that everything reduces to that. What I'm saying is that human experience is very much like traversed by this thing, right? And even if you go to the foundations of Boolean logic and like truth and falsity and like, or falsehood in humans, like at the end of the day, really it comes down to your own personal cognitive dissonance, right? Like if someone, like the idea of truth and falsehood in conversation with other humans, right? At the end of the day, it has to do with like, oh yeah, I created the expectation that someone told me that this is true. Like there's a red bird outside. Like I created this expectation in my mind, and then I go outside and I see a whatever, a blue horse or something. It's like, wait, that wasn't a red bird. So you get a moment of cognitive dissonance, like your mind state differs from what you see, and then you go back and you say, well, what the information that I was told was false, because you experience that moment of discomfort or like cognitive dissonance. And like, so humans are like, this is permeated to everything we do, right? Obviously, most of the time you want to think that you're neutral and you're not reacting emotionally to that. But I would say like Boolean values are based very much on that. So this idea of outputs being something more like RGB instead of true or false, or red or black and white, has to do with a change in kind of mentality, right? Like you have to think that you're gonna filter the world in with a different angle. Like you're not gonna be focused on things that you can react to in a way that just puts you either more or less towards it, right? Which is why I think space helps a lot. That's what I meant. That's what I meant when I said you need to go to higher dimensions of win state values, right? Like if your win state is constrained to living in one dimension, which is basically where you can map your concentrations of hormones that make you angry or make you happy, like which is quite a linear space. If you suddenly add another axis, it doesn't have to be even different from being angry or happy, but it can be like being happy and angry, or being also whatever, like hungry and or full or something, like it doesn't matter. But the point is, the moment you add more dimensions to your cognitive measure state, then suddenly you have more domain to get. And the question you asked, Nick, was exactly what we were working on a couple of years ago. And yeah, it's very interesting, very weird, very hard to think about. Like, it's like saying, someone asked me if they ate 2 bowls of cereal yesterday, and maybe they want to know if that's true or false, and your answer is red. It's like, yeah. So it's not you can imagine a world where we have a 3-valued logic where none of the values is true or false. This is just like red, blue, green, whatever that means. And who knows? It's a different world, and who knows if it's powerful. Actually, these kinds of models where you would have
it
like
reminds me of quantum chromodynamics, because you have
Say it again?
all these quantum chromodynamics,
Yeah.
right? So
Uh-huh.
you have like 3 fields, and it's not like binary or anything. It's like
But they even 3-valued logic is a thing. So
yeah, ternary
Yeah,
logic.
I think 3-valued logic assumes that 2 of the 3 values is true and false.
It's like true, false, and undecided. Is one way
Maybe.
to have.
I don't know.
Maybe.
Yeah,
So-
yeah. And so that's what I meant, that it is logical values. There are more than 2, and none of them are kind of mapped to true and false. Because that's the whole thing. I mean, the whole thing is that you're not opposing like conventional logic. What you're saying is, wait, I'm gonna add. It's almost like, true and false is like seeing the world in black and white. Like, it's like the analogy is very powerful, right? Because black and white is very, very good for most things we need. Right? If you don't have color vision, your life is essentially unchanged. Right? You can go about your life, no problem. But sometimes there are some aspects of life that get highly enriched or get much easier to process or much easier to model when color is involved, and you have color, and you can add that extra dimension quite literally on top of the grayscale dimension. And so this is what we're talking about here. And yeah, it's kind of a funny thing. I don't know. I haven't really ever done much with it, because it's so strange to think about that you want to change all your functions to be valued in a 3-element set. I mean, you no longer you don't know what to do exactly, right? Like it's exactly the situation where all your problems, the answers to your questions are always going to be of the kind: are you closer to red, blue, or green, instead of are you true or false, or are you more of this or that? It's always going to be, are you closer to this or that? And I think it works really well for things that, for human beings, there are many things that work really well with that, which is like, in arts or in things that are not easy to quantify, usually having this kind of symbolic but non-quantitative measurements are reasonable, which oftentimes just reduces to like having tags or something like that. It's like, can you tag this thing with this or this or that, or these people playing together this game had the flavor of this. It was a red game, or this other game they played was a green game.
I have a comment here from WWKK about 7 a Jane logic, Jainism. 7 valued logic formalism.
Oh wow.
Yeah.
Yeah.
It's pretty interesting.
Jumping right ahead into higher dimensions very quickly. Yeah, because like this 3 valued stuff you can still maybe visualize with like black and white one axis, and then you need maybe another axis to throw like orthogonal colors. So they maybe leave on one orthogonal axis or a couple of them. But if you want 7, like you have to go at least to like, I don't know, 4 or 5 dimensions, I guess.
I wonder what that's actually correct, because logic usually is formal thing, right? You have to come up with axioms about the 7 values, right? It seems to me if you have some notion of logic, it's so many things that human even can comprehend. It's too easy to make it like not undecidable, but just simply incorrect, right? Falsifiable.
Yeah, falsifiable. Yeah. No, that's interesting. I don't know, like having
it's like writing a constitution. There's always some kind of and laws. There's always some way of to find a contradiction there.
Yeah. Exactly. Interesting questions. Who's getting into the weeds of computational science? Kind of fundamental questions that we get into. It's nice to get them resurfaced.
Yeah, and what's nice about this is the potential directions all feed off of each other, because this informs machine learning. It informs ways to think about economics from like a ecology perspective, biology. It's really cool how these things have multiple use cases across various fields.
Oh, absolutely. Yeah.
Physics even, it's really cool.
Yeah. It's really cool.
Probability. Okay, cool. I need to jump off now. Was there anything more specific you wanted to cover from your side, Nick?
No, I think we went through all of this. I think Steven's gonna do the whole reading of this block at some point anyway. So there's no way, there's no point in spoiling that. So, or you can just read it yourself.
Yeah.
Great. Yeah, and well done on doing the work behind this as well. This is impressive.
Great work, Nick. Yeah.
Yeah, and the rest of the team.
Many people. Brad, Richard.
Yeah.
Thanks, Dugan.
Yeah, Richard was also involved. Yes.
Dugan did some stuff. Actually, there was a few things from Dugan's side you might want to show at some point.
Oh, I think I helped with like one diagram, like towards the end of it.
Okay, but you're doing a live stream tomorrow, Dugan. So everyone tune in. Yeah,
I'll be talking about Penrose tilings and other aperiodic tilings on live stream tomorrow. So watch out for that.
Nice, amazing. Well, looking forward, everyone.